Section 1 Introduction. Our introductory discussion delves into the impact of large language models, LLMs, on the realm of natural language processing, NLP. These models have demonstrated extraordinary capability across various language tasks. However, they're not without their drawbacks. For instance, their billions of parameters call for hefty computational resources. We've been striving to level the playing field and make LLMs accessible to a broader audience. As a part of this mission, we've been focusing on minimizing their computational demands. A key development in this area has been the technique of model quantization. This process involves converting parameters into smaller bit-level representations, which has resulted in substantial resource savings. Alongside model quantization, there's a second strategy for reducing model size known as network pruning. This technique involves reducing the size of the network by setting specific weights in the model to 0. Although this method has been widely used for compressing neural networks, it hasn't been as extensively used for LLMs. The reason behind this discrepancy could be attributed to the fact that pruning methods usually require retraining, training from scratch, or an extensive iterative process. Given the vast computational resources that LLMs require, these methods aren't practical. Even sparse GPT, a recent LLM pruning method that doesn't require retraining, still demands a computation-heavy weight update process. The challenges in pruning LLMs don't end at retraining and weight updates. It would be reasonable to assume that using popular pruning methods, we could find a decent starting point for retraining. However, research suggests that this isn't the case. For instance, magnitude pruning, a tried and tested pruning method, doesn't perform well on LLMs with a low level of sparsity. This reveals that despite having 100 to 1,000 times more parameters, LLMs are significantly harder to prune directly. In our research, we tackle this problem by proposing an uncomplicated yet efficient approach, which we've named Wanda, short for pruning by weights and activations. This method successfully prunes LLMs to high degrees of sparsity without having to modify the remaining weights. Our approach is inspired by a recent study that found a small subset of hidden state features in LLMs that are unusually large in magnitude. We discovered that the standard weight magnitude pruning metric could be enhanced by input activations, providing a surprisingly effective means of evaluating weight importance. Specifically, we've devised a novel pruning metric. In this metric, each weight's value is determined by the product of its magnitude and the norm of the corresponding input activations. We estimate this using a small dataset for calibration. Our method uses this metric to induce sparsity in pre-trained LLMs. It does so by comparing weights locally within each output of linear layers and discarding lower priority weights. Not only is our approach computationally efficient, but it can also be performed in a single forward pass and requires minimal memory overhead. We've put Wanda to the test on Llama, one of the most effective open-sourced LLM families. The results have shown that Wanda can identify efficient sparse networks directly from pre-trained LLMs, without any need for retraining or weight updates. Moreover, Wanda surpasses magnitude pruning by a considerable margin, matching or outperforming a recent LLM pruning method while requiring lower computational resources. Our hope is that our work will serve as a reference point for future studies in this field. We also encourage further exploration into understanding sparsity in LLMs. Section Summary. Large language models, LLMs, have remarkable performance but require significant computational resources. Model quantization and network pruning are popular approaches for compressing neural networks, but pruning has received relatively little focus in compressing LLMs due to the need for retraining and weight update. The Wanda approach introduces a novel pruning metric that uses the product of weight magnitude and the norm of corresponding input activations to induce sparsity in pre-trained LLMs, without any retraining or weight update, and outperforms magnitude pruning in a recently proposed method for pruning LLMs while requiring lower computational cost. Section 2 Preliminaries. In this section, we will lay the groundwork by explaining two key concepts: magnitude pruning and emergent large magnitude features. Magnitude pruning is a common method used to create sparsity, or a significant number of zero values, in neural networks. This technique stands apart from others because it focuses on eliminating individual weights, not based on their position or role, but according to their size. If a weight's value is below a certain limit, it gets discarded. How we determine this limit typically involves comparing the weights across the entire network or within individual layers. Even though it sounds quite straightforward, magnitude pruning has proven incredibly useful. It allows us to discover extremely sparse neural networks, making it an effective baseline strategy for sparsification. On the other hand, emergent large magnitude features are unique to transformer-based, large language models. Once these models attain a certain size, typically around 6 billion parameters, something fascinating happens. A handful of hidden state features begin to stand out with sizes significantly larger than the rest. This phenomenon of outlier features has been confirmed in various large language models. These exceptional features are intriguing for a few reasons. First, their sizes are notably large, almost 100 times larger than the average hidden state values. Second, these features are typically sparse and appear in specific feature dimensions. The most important point is that these outlier features are critical for the model's predictive power. If we were to set these features to 0 during the prediction stage, the language model's performance would drastically decline. Section summary. Magnitude pruning is a simple technique that removes individual weights from neural networks based on their magnitudes, resulting in extremely sparse networks. Emergent large magnitude features are specific to transformer-based large language models and refer to a small set of hidden state features with significantly larger magnitudes than the remaining ones. These outlier features are essential for the predictive capability of LLMs, and their removal results in significant degradation of language modeling performance. Section 3. Pruning by weights and activations. In this section, we delve into the specifics of our proposed pruning technique named Wanda, which stands for Pruning by Weights and Activations. Wanda involves two main components, a novel pruning metric and a comparison of weights on an output-by-output basis, both of which are vital for effectively pruning large language models, LLMs. Firstly, let's talk about our proposed pruning metric. Traditional pruning techniques often focus only on the weights and disregard the input activations, but we're introducing a new metric that considers both. To illustrate why this is important, let's take an example of a neuron with two inputs and corresponding weights. Suppose you're tasked with removing one weight so as to have a minimal impact on the output. If you were using the standard magnitude pruning method, you'd be inclined to remove the weight with the smaller absolute value. However, we've found that in LLMs, the input features can vary significantly in scale, meaning that removing the weight with the smaller magnitude could potentially result in a large change in the output. Therefore, we propose a new pruning metric specifically for LLMs, which combines both the magnitude of the weights and the norms of the input features to determine the importance of each weight. We've found that the Euclidean norm, or L2 norm, works best for measuring the magnitude of input features. The importance of a weight is then calculated as the product of the absolute value of the weight and the L2 norm of its corresponding input feature. Another key aspect of our approach is that we compare weights on an output-by-output basis, rather than comparing all the weights in a layer or in the entire network. We've found that this local comparison results in more effective pruning of LLMs. We believe that this method of comparing weights prevents uneven pruning across different output features, which seems to be particularly beneficial for LLMs. Now, let's look at the actual implementation. Wanda can be easily integrated within a single forward pass of the LLM model. We estimate the L2 norms of the input features with a set of calibration data and then compute our pruning metric for each weight. Notably, our approach doesn't require any further weight updates or training once the pruning is done. In addition to unstructured sparsity, Wanda can also be adapted for structured M sparsity, where at most n out of every m contiguous weights are non-zero. For this, we only need to compare every m consecutive weights connected to an output using our pruning metric. Reflecting on the context of previous works, our pruning approach has some similarities with sparse GPT and the pioneering optimal brain damage (OBD) technique. However, Wanda simplifies the weight importance computation, eliminating the need for computing any matrix inverses, and it can be viewed as applying a process similar to OBD to each neuron. In summary, our proposed pruning technique, Wanda, has several attractive properties. 1. It is simple, like the magnitude pruning methods of the past, and does not require gradient computation or Hessian inverses, yet it's highly effective for pruning pre-trained LLMs. 2. It can be executed with a single forward pass of the LLM and does not require iterative procedures. In fact, it is 300 times faster than sparse GPT in practice. 3. Unlike sparse GPT, Wanda doesn't need weight updates after pruning, suggesting that LLMs have precise, sparse subnetworks rather than vague ones in the vicinity of the original weights. Section summary. The proposed pruning approach, Wanda, incorporates both weights and input activations into the computation of weight importance, which is crucial for pruning LLMs effectively. The pruning metric is designed explicitly for LLMs to handle the limitation of magnitude pruning, and the pruning granularity is set on a per-output basis, which helps prevent imbalanced pruning across different output features. Wanda can be implemented and integrated seamlessly within a single forward pass of the LLM model, and it requires no weight update, making it highly effective and efficient in discovering sparse networks in pre-trained LLMs. Section 4. Experiments. We've conducted various experiments to evaluate our model, Wanda, specifically by testing it on the Llama model family. These are a set of transformer language models that come in different sizes, typically labeled as Llama 7B, Llama 13B, Llama 30B, and Llama 65B. We used our pruning technique on all 4 models. However, it's worth mentioning that our approach can be used on any model architecture that has many linear layers, including other transformer-based language models. You can find results for other language model families in the appendix. To evaluate the effectiveness of our pruned models, we first check their language modeling ability by computing the perplexity on a separate validation set. Perplexity is a commonly used measure in language models that gives an indication of how well the model predicts a sample. To be more specific, we use the Wikitext validation set, which is a standard in the field. Moreover, we also checked the model's zero-shot performance using a public evaluation tool called Eleuther AILM Harness. This was done on 7 common sense benchmarks, namely Boole Q, RTE, Hella Swag, Wino Grande, Arc Easy and Challenge, and OpenBook QA. We then reported the accuracy of each benchmark and the overall mean accuracy. To compare the effectiveness of our method, Wanda, we tested it against 2 prior pruning methods. The first one is magnitude pruning, a straightforward yet powerful method that discards weights based on their size. It has been shown to perform better than many other pruning methods. The second one is sparse GPT, a more advanced pruning technique that solves a layer-wise reconstruction problem and iterates between weight removal and weight updating at each layer. As far as we know, this is the only pruning method so far that has proven to work with language models. Both our model, Wanda, and sparse GPT require calibration data to make some statistical estimations. To keep our experiments consistent, we used the same calibration data set as sparse GPT, which consists of 128 sequences, each made up of 2048 tokens. In all pruning methods, we imposed a uniform sparsity on all layers and did not perform any subsequent retraining. We excluded the first embedding layer and the final classification layer, as is common practice in pruning transformers. We mainly induced sparsity through unstructured pruning. However, in light of potential requirements for practical speedup, we also evaluated unstructured N/M sparsity, specifically looking at 4-8 and 2-4 sparsity patterns. Section summary. The paper evaluates the Wanda pruning method on the Llama model family, consisting of various transformer language models. The performance of pruned networks is measured by perplexity and zero-shot ability on 7 common sense benchmarks. Wanda is compared to 2 prior pruning methods, magnitude pruning and sparse GPT, and the setup includes uniform sparsity imposed for all layers and unstructured pruning. Section 4.2 Language Modeling. In this section, we're exploring language modeling in the context of unstructured sparsity. We've applied this to all of our Llama models, trimming them down to a level of 50% unstructured sparsity across all methods. If you look at the data in our table, you'll see that without modifying any weights, our approach, which we call Wanda, performs much better than the commonly used magnitude pruning approach. To illustrate this, let's consider the Llama 7B model. Here, Wanda is capable of identifying sparse networks with a perplexity score, a measure of predictability, of 7.26. This is a substantial improvement over the baseline score of 17.29 achieved with magnitude pruning. Generally, our method performs just as well, or in many cases even better, than the previously used method, sparse GPT, which is based on reconstruction. We also investigate the application of structured N/M sparsity, which by its nature is more restrictive than unstructured sparsity. As a result, you'd expect this type of structured sparsity to yield poorer results. When we examine the results for 4-8 and 2-4 structured sparsity, presented in our table, it's apparent that Wanda can adapt quite well to this type of structured sparsity. Regardless of whether we're dealing with 4-8 or 2-4 sparsity, our method consistently identifies highly efficient sparse subnetworks, frequently outperforming the baseline methods, especially when we use larger models like the 30B and 65B versions. It's worth noting that in some instances, Wanda's results are only slightly better than, or similar to, those of sparse GPT. This could be linked to the fact that our pruning metric shares an indirect relationship with the OBS reconstruction error, as we discussed and clarified earlier in the paper. Although the improvements in perplexity scores over sparse GPT might not seem huge, it's important to remember that Wanda is simpler and more efficient computationally. Finally, we carried out experiments with different levels of unstructured sparsity, the results of which can be seen in our figure. It becomes clear that both Wanda and sparse GPT exhibit similar trends, with the perplexity score rising as the sparsity level increases. However, the degradation trend is far more severe with magnitude pruning. Section summary. The paper discusses the performance of Wanda, a new pruning approach, in comparison to established methods for unstructured and structured sparsity patterns. Results show that Wanda outperforms magnitude pruning and performs on par with or better than sparse GPT. Additionally, Wanda is simpler and more computationally efficient than sparse GPT. Varying levels of sparsity for unstructured pruning were also tested, with Wanda and sparse GPT showing similar trends of perplexity increase as sparsity level increases, while magnitude pruning displayed a more severe degradation trend. Section 4.30 Shot Tasks. In Section 4.3, we discuss the performance of pruned models on what we call zero-shot tasks. These tasks are evaluated using a method called prompting. We present the results in an organized table where the models have been reduced to 50% sparsity, meaning only half of the connections remain in the network. On average, and across the 7 tasks we've examined, the Wanda pruning method is successful at identifying useful pruned networks. We found that it holds up well when compared to the baseline methods we used for comparison. One interesting observation is that as the network size increases, the performance drop compared to the original, unpruned network continues to shrink. For individual task performance, we noticed that our Wanda method consistently outperforms other methods in specific tasks, namely HelloSwag, ArcC, and OpenBookQA, across all llama models. However, for the remaining tasks, we could not definitively determine a superior method. Section 4.4 shifts focus to the speed at which the pruning process takes place. In theory, our Wanda method has a lower computational complexity than another method, sparse GPT. To test this, we compared their actual pruning speeds. We timed only the pruning process itself, excluding the shared forward pass process, on NVIDIA A6000 GPS. The results, presented in a table, show that Wanda has an almost negligible time difference when compared with sparse GPT. This quick speed is especially useful when pruning needs to be done in real time, like when we need to process different data samples with varying levels of sparsity. Section summary. The paper evaluates pruned models on downstream zero-shot tasks using prompting and finds that the Wanda method is competitive with baseline methods, especially for tasks such as HelloSwag, ArcC, and OpenBookQA. The pruning speed of Wanda is also found to be faster than sparse GPT, making it useful for real-time pruning needs. Section 4.5 Ablation Study. In Section 4.5, we carry out an in-depth analysis on 3 different aspects of Wanda to answer these questions. 1. How does the choice of pruning configurations, like the pruning metric and pruning granularity, impact the pruned model's performance? 2. How resilient is our pruning method to calibration samples? 3. Can Wanda be merged with an OBS-based weight update, similar to what is used in sparse GPT? To conduct these studies, we prune the Llama 7B model until it reaches an unstructured 50% sparsity level. We then assess the resulting model's performance, particularly its complexity in handling language, by evaluating its perplexity on Wikitext. To begin with, we differentiate Wanda from preceding methods based on its unique pruning metric and granularity. We then carry out a range of experiments to evaluate the effectiveness of these metrics and granularities. We examine 3 different pruning metrics detailed in a table, where sparse GPT employs a local granularity level within a layer. Here, weights associated with 128 consecutive input channels are grouped together. On the other hand, Wanda groups weights associated with a single output channel. We test 2 block sizes, 128 and 1, and the choice between input-output for our ablation study. To denote the local pruning granularity level, we use the notation input-output block size. For instance, input 1. For this specific experiment, we focus on metric and granularity by not performing a weight update for sparse GPT. Results indicate that Wanda's default configuration delivers the best pruned model with a perplexity of 7.26. Interestingly, when using the magnitude metric and comparing weights of the same input neuron, input 1, we achieve a perplexity of 8.86. This is noticeably better than other granularity options. Under this granularity, 3 methods produce similar pruning results, because the input is the same, hence weight ranking only relies on weight magnitude. This underscores the significance of choosing the right pruning granularity when pruning large language models, LLMs, even for the traditional magnitude pruning. Another important aspect we need to examine is the robustness of our method to calibration samples. We rely on a set of calibration data to gauge the input statistics of each layer. It's crucial to understand how the calibration data selection impacts the final pruned networks. We use 5 different calibration datasets, each with the same size, 128, taken from different shards of C4 training data. Our results show the pruned network's complexity from these 5 calibration sets are very similar, with an average perplexity close to 7.26, which we previously reported. This suggests that the performance isn't overly reliant on the exact selection of the calibration data. We further vary the number of calibration samples by selecting different sample sizes from 1 to 256. As the size of the calibration data changes, we see a clear difference in trends, with Wanda proving to be more resilient when fewer calibration samples are used. Remarkably, even with a single sample, our method delivers a pruned network with a perplexity of 7.66. This could be attributed to the fact that it's simpler to estimate the input norm statistics than the full inverse Hessian of the local layer-wise reconstruction problem. Finally, we examine whether we can improve the pruned models by incorporating the OBS weight update process proposed in sparse GPT. We use this OBS weight update procedure on the retained weights from both magnitude pruning and our method, Wanda, and evaluate the perplexity on both the calibration data and the validation data from Wikitext. The result verifies the effectiveness of the weight update procedure on magnitude pruning, where it significantly improves perplexity on both data splits. However, when the pruned model is obtained by our method, Wanda, this process doesn't bring any improvement. Instead, it leads to a slight increase in perplexity, from 7.26 to 7.32, on validation data. This suggests that in this case, the updated model may overfit to the calibration samples. Section summary. The authors conducted an ablation study on Wanda to investigate the impact of pruning configurations on model performance, the robustness of the pruning method to calibration samples, and the integration of Wanda with OBS-based weight update as used in sparse GPT. They found that Wanda's default configuration delivers the best pruned model, and the performance does not depend too heavily on the exact selection of calibration data. However, incorporating the OBS weight update process proposed in sparse GPT did not improve the pruned model obtained by Wanda. Section 5 Analysis. In this section, we'll first explore whether Wanda has broader applications beyond just large language models, LLMs. We'll then delve into preliminary results from using parameter-efficient fine-tuning techniques to offset the drop in performance that occurs during the pruning process. 5.1 Wanda's broader applications beyond pruning LLMs. Although our main focus is on pruning LLMs, Wanda's effectiveness prompts us to ask a crucial question. How does Wanda compare to the commonly used method of magnitude pruning on tasks where the latter is traditionally applied? To investigate this, we carry out a study using ImageNet-1K, a widely accepted baseline for image classification tasks where magnitude pruning has been extensively researched. We consider 2 modern vision architectures for our analysis, Convenext and Vision Transformer, VIT. We chose these 2 architectures for a couple of reasons. Firstly, since LLMs are based on transformers, we want to check if our findings on LLMs still hold for transformers applied to other tasks. And secondly, given that our evaluation is centered on image classification, we are curious to see how these techniques perform with ConveNet models, with Convenext serving as a representative example. We work with 2 pre-trained ImageNet-1K models, Convenext B and VIT B, boasting top 1 accuracies of 83.8% and 81.8% respectively. We limit our pruning to the linear layers only, which, in the case of Convenext, includes equivalent 1x1 convolution layers. For both models, we find that pruning evenly across all layers tends to yield better results than pruning on a per-output basis. Therefore, we compare our newly proposed pruning metric with the traditional magnitude metric by pruning on a layer-by-layer basis. The results indicate that our innovative pruning metric outperforms magnitude pruning, particularly at high sparsity levels, for example, at 70% and 80%. However, we noticed that the accuracy differences between pruned networks can often be compensated for by retraining the model for a few epochs. This suggests that Wanda might be more fitting for scenarios where retraining isn't computationally viable, as is often the case with LLMs. Section summary. The effectiveness of Wanda in pruning LLMs raises the question of whether it can be applied to other tasks. The authors conduct a study on ImageNet-1K using Convenext and Vision Transformer architectures and find that pruning uniformly on a per-layer basis using their proposed metric leads to better results than magnitude pruning, especially at high sparsities. However, retraining for a few epochs can mitigate differences in accuracy, suggesting that Wanda may be more suitable for cases where retraining is not feasible, such as in LLMs. Section 5.2 LoRA Fine-Tuning. In this section, we'll first explore whether Wanda has broader applications beyond just large language models, LLMs. We'll then delve into preliminary results from using parameter-efficient fine-tuning techniques to offset the drop in performance that occurs during the pruning process. 5.1 Wanda's broader applications beyond pruning LLMs. Although our main focus is on pruning LLMs, Wanda's effectiveness prompts us to ask a crucial question. How does Wanda compare to the commonly used method of magnitude pruning on tasks where the latter is traditionally applied? To investigate this, we carry out a study using ImageNet-1K, a widely accepted baseline for image classification tasks where magnitude pruning has been extensively researched. We consider two modern vision architectures for our analysis, Convenext and Vision Transformer, VIT. We chose these two architectures for a couple of reasons. Firstly, since LLMs are based on transformers, we want to check if our findings on LLMs still hold for transformers applied to other tasks. And secondly, given that our evaluation is centered on image classification, we are curious to see how these techniques perform with ConveNet models, with Convenext serving as a representative example. We work with two pre-trained ImageNet-1K models, Convenext B and VIT B, boasting top 1 accuracies of 83.8% and 81.8% respectively. We limit our pruning to the linear layers only, which, in the case of Convenext, includes equivalent 1x1 convolution layers. For both models, we find that pruning evenly across all layers tends to yield better results than pruning on a per-output basis. Therefore, we compare our newly proposed pruning metric with the traditional magnitude metric by pruning on a layer-by-layer basis. The results indicate that our innovative pruning metric outperforms magnitude pruning, particularly at high sparsity levels, for example, at 70% and 80%. However, we noticed that the accuracy differences between pruned networks can often be compensated for by retraining the model for a few epochs. This suggests that Wanda might be more fitting for scenarios where retraining isn't computationally viable, as is often the case with LLMs. Section Summary. The section discusses the use of parameter-efficient fine-tuning (PEFT) techniques, specifically LoRA, to recover the performance of pruned LLM models. The study shows that it is possible to restore the performance of pruned Llama 7B with a non-trivial amount, reducing zero-shot wikitext perplexity from 7.26 to 6.87, while maintaining the sparsity level at around 50%. The work is related to existing pruning methods, pruning with limited data, and emergent properties of LLMs.